Have you ever noticed how, like, sometimes when one thing changes, it can have, like, a domino effect,
Uh-huh.
and it ends up changing something else too?
Yeah, yeah, for sure.
Like, if you're making tea for more people, suddenly you need way more sugar and milk.
Totally.
Yeah.
Yeah, and it's like it's
Yeah.
not just about adding more, it's about adding the right amount more.
Right, exactly. Like everything's connected. Or think about like packing a suitcase, the more carefully you pack, like the more you can fit in.
Oh yeah, for sure. Maximizing that space.
Yeah, exactly. And we've got some really interesting stuff to dive into today, all about this idea.
Right, these connections, these
Uh-huh.
relationships between things.
Yeah, like how things change together. And for this deep dive, we're focusing on two very specific relationships.
Uh-huh. The heart of it all, direct and inverse proportion.
Exactly. And I think this is going to give us like a really neat framework
Yeah,
to like understand so many real world things.
totally, without getting bogged down in the math.
Right,
It's
exactly.
about the concept.
Okay, so first up, direct proportion. So this is when one thing increases, the other increases at the same rate.
Uh-huh.
And it's like this perfectly balanced ratio.
Yeah, it's all about that constant ratio. That's the key.
Like a seesaw that stays level.
Exactly.
So the example that you sent was about sugar.
Okay. Yeah.
If 1 kilogram of sugar costs 36, then 3 kilograms will cost 108.
Right, because you're essentially tripling the amount.
Yeah.
So you triple the cost.
Exactly. The price per kilo stays the same.
Uh-huh. 36.
Yeah, 36.
That's that constant ratio.
So how do we, like, express that mathematically then?
Well, so if we call one quantity x and the other y,
Okay.
then in direct proportion, x divided by y will always give you the same number.
Okay.
We can call that k our constant.
Okay.
So x, y equal k. Or you could also think of it as x being a multiple of y.
Okay.
X, k, got it.
Got it.
Your material also pointed out that if you've got two sets of values,
Okay.
say a1 and y1, and then by 2 and y2, the ratio by 1, y1 will be the same as the ratio by 2, y2.
Okay.
It's all about that consistent relationship.
So it's not just about them increasing at the same time, it's
It's that the ratio stays the same.
the ratio stays the same the whole time.
Exactly.
Okay, got it.
It's a bit more specific than just things going up together.
Okay, I'm with you. And there was another example in the material about fuel consumption.
Oh, yeah.
Like in a car,
Uh,
if you have 4 liters of petrol, you can go 60 kilometers. But if you have 12 liters, you can go 180 kilometers.
right. So again, you're tripling the fuel and you're tripling the distance.
Yeah.
But the important thing is the distance you get per liter that stays the same.
Yeah.
That's your constant. In this case, it's 15 kilometers per liter.
Got it. So in both these cases, when one quantity increases, the other one follows suit in this like very predictable way.
Yeah. And it all comes down to that stable ratio. That's the hallmark of direct proportion.
I like the hallmark.
That's what you're looking for.
So there was also this do this section with a clock example.
Oh, yeah, that's a good one.
I thought this was super helpful. So imagine a clock. The minute hand is at 12.
Okay.
And then as time passes, the angle of the hand changes.
Right. It's constantly moving.
Yeah. So the table showed that after 15 minutes, the angle is 90 degrees. 30 minutes, 180 degrees.
Yep.
45 minutes, 270 degrees.
Makes sense.
And then a full hour, 360 degrees.
Right back where it started.
So if you look at like the relationship between the time pass, let's call that T,
Right.
and the angle A, the ratio TA is always the same.
Right. It's constant.
Like 15 over 90 simplifies to 1/6.
Yep.
30 over 180 is also 1/6, and so on.
That consistent ratio, that's the key.
Yeah, that's like the direct link that we're talking about.
Exactly. That's how you know it's direct proportion.
And you know what else the material pointed out?
What's that?
If you compare two different times, like 15 minutes and 30 minutes,
Okay.
which is a ratio of 1 to 2. The corresponding angles, 90 degrees and 180 degrees, also have the same ratio, 1 to 2.
Right. So the ratios are matching up.
It's all proportional.
It's all beautifully connected.
But then, the material threw in this, like, curveball.
Oh, yeah. What was that?
It asked about the ages of a friend and their mother.
Okay. Yeah, I remember that.
It said, think about their ages now, 5 years ago and 5 years from now,
Mm-hmm.
and then compare the ratios of their ages at those different points in time.
And what do you notice?
Well, even though both the friend's age and the mother's age are increasing right as time goes on,
Yeah.
the ratio between their ages is actually changing.
It's not constant.
Not constant.
Yeah.
So, for example, if the friend is currently 10
Okay.
and the mother is 40,
A big difference.
that's a ratio of 1 to 4, right?
Right.
But 5 years ago, they were 5 and 35,
Okay.
which is a ratio of 1 to 7.
So the ratio shifted.
And then in 5 years, they'll be 15 and 45,
Uh-huh.
a ratio of 1 to 3.
So even though both ages are increasing, the relationship between them is not directly proportional.
Yeah, it's not staying consistent.
It's not about things simply going up or down together.
You got it.
It's about that constant ratio. It's the real test.
The hallmark.
Exactly.
So just because two things increase or decrease together, it doesn't automatically mean they're in direct proportion.
No.
Ah.
It's tempting to think that, but you got to check that ratio.
Okay, so then there's this try these section.
Oh, yeah, where we get to put this into practice.
Exactly, and it gives us 3 sets of x and y values and asks if they show direct proportion.
Okay, let's dive in.
So in the first set, x is going down from 20 to 2,
Okay.
and y is going down from 40 to 4.
Okay, so they're both decreasing.
Yeah, so if we look at the ratio of y to x for each pair,
Let's see, 40 over 20, 34 over 17, 28 over 14, and so on.
do they all equal the same thing?
They do. They all equal 2.
2.
So yes, this is a direct
If
proportion.
it passes the test.
It does. That consistent ratio is the key.
Okay, so on to the second set.
Right. What do we have here?
This time x is going up from 6 to 30, and y is also increasing from 4 to 28.
Okay, so both increasing. Let's see about that ratio.
So 4 over 6, that's 2/3.
Okay.
But 8 over 10 is 4/5.
Ah, so right there we see the ratios aren't the same.
Busted.
Even though X and Y are both increasing,
Yeah.
they're not doing it proportional.
Not a direct proportion.
Yep.
Okay, last one.
Bring it on.
X increases from 5 to 20,
Okay.
and y also increases from 15 to 100.
Right. Let's check those ratios.
15 over 5 is 3. 24 over 8 is 3. 36 over 12 is 3.
So far, so good.
But then 60 over 15,
That's 4.
that's 4.
Inconsistent.
It's not a direct proportion.
Nope, because that ratio isn't constant for all the pairs.
Okay, I think I'm starting to get this, like, that constant ratio is super important.
It's the defining characteristic of direct proportion.
Okay, so then your materials moved on to this really interesting comparison of simple versus compound interest.
Yeah, that's a good one. It gets a little more complex.
Yeah, it starts with 1,000 rupees and an 8% annual interest rate.
Okay, standard stuff.
So for simple interest, the formula is principal times rate times time divided by 100.
Right.
So with the principal and the rate fixed,
Mm-hmm.
as time increases, the simple interest earned will also increase at a steady pace.
Yeah, it's a very straightforward linear relationship.
Yeah. So in this case, simple interest is directly proportional to time.
Right. Double the time, double the interest.
But then there was this really interesting question.
Yeah, what about compound interest?
Yeah. Does
Yeah.
that show the same direct relationship?
It's a bit trickier.
It's trickier because of that compounding effect, right?
Exactly. Compound interest earns interest not just on the initial amount, but also on the interest that's already accumulated.
Oh, so it's like a snowball effect.
Exactly. It grows exponentially, which means the increase isn't happening at a constant rate relative to time.
Right. It's accelerating.
So it's not as straightforward as simple interest?
Nope. It's a bit more dynamic.
Okay, so we went through a bunch of solved examples.
Yeah, let's break those down.
I found these really
So
helpful.
me too. They make it so much clearer.
So the first one was about buying cloth.
Okay. Classic example.
If 5 meters of cloth costs 210,
Uh-huh.
how do you figure out the cost of, say, 2 meters?
Well, since the cost goes up proportionally to the length you buy,
Right.
we can use our direct proportion knowledge.
Okay.
You can set up a relationship cost of 2 meters over 2 meters equals 210 over 5 meters.
Okay.
And when you solve for the unknown cost, you get 84.
84.
And the material showed you how to do this for other lengths, too.
Yeah, 4 meters, 10 meters, 13 meters.
It's all about applying that same principle.
So what are we really doing here when we set up that equation?
We're leveraging that consistent ratio that defines direct proportion by 1y1 equals by 2y2.
In this case, X is the length of the cloth, and Y is the cost.
Got it.
And that balance, that equation will always hold true for any two lengths and their corresponding costs in a direct proportion.
Makes sense.
A powerful tool.
Okay, the next example, this one involved an electric pole.
Okay.
So a 14-meter electric pole casts a 10-meter shadow.
Mm-hmm.
The question was, if a nearby tree casts a 15-meter shadow under the same conditions, how tall is the tree?
Good question.
So here's the principle. The height of an object is directly proportional to the length of its shadow.
At a given time of day, right?
Yeah,
Because the angle of the sun is the same.
exactly.
That's important.
So we can set up a proportion.
Okay.
14 meters over 10 meters equals height of the tree over 15 meters.
And when you solve for the tree's height,
What do you
you
get?
get 21 meters.
21 meters.
That's a tall tree.
So again, it's that underlying ratio.
Right? The ratio of height to shadow length.
Yeah.
It stays the same for both the pole and the tree.
It's so cool how you can use like one piece of information
And that constant ratio.
to figure out the other.
It's a good puzzle piece.
Okay. Then there was a problem about paper,
Okay.
about the weight of paper sheets.
Right.
We were given that 12 sheets of thick paper weigh 40 grams.
Okay.
The question was, how many sheets would weigh 2.5 kilograms?
So first we got to make sure our units match up.
Right. 2.5 kilograms is the same as 2,500 grams.
Exactly.
Okay. So since the number of sheets is directly proportional to their weight, we set up our proportion.
Okay.
12 sheets over 40 grams equals number of sheets over 2,500 grams.
And what do you get when you solve for the unknown number of sheets?
750 sheets.
750 sheets.
Yeah.
That's a lot of paper.
Yeah.
And, your material also showed another way to think about this.
Oh, really?
Yeah, by finding the constant of proportionality.
Yeah.
Yeah, K.
Okay.
In this case, K would be the number of sheets per gram, which is 12 over 40 or 3/10.
Okay.
Then to find how many sheets weigh 2,500 grams, you just multiply K by the new weight. 3/10 times 2,500 equals 750.
So you get the same answer?
Exactly. Both methods work.
That's so cool.
They just offer different ways of looking at the same concept.
Okay, and then there was the train example.
Oh, yeah, the train speed and distance problem.
So a train is going at a steady speed of 75 kilometers per hour.
Okay.
And we need to figure out how far it'll go in 20 minutes.
Okay.
And how long it'll take to cover 250 kilometers.
Got it.
So because the speed is constant, the distance covered is directly proportional to the time traveled.
Yeah, it makes sense.
But for that first part, we got to watch our units.
Yeah.
20 minutes is 1/3 of an hour.
Right.
So distance equals speed times time 75 kilometers per hour times 1/3 hour.
And that gives you
25 kilometers.
25 kilometers.
And then for the second part, we can use our trusty proportion. 75 kilometers over 60 minutes equals 250 kilometers over time in minutes.
Okay.
And that works out to
200 minutes.
200 minutes or 3 hours and 20 minutes.
So that's a classic example of how direct proportion is used all the time in these situations with speed, distance, and time.
Yeah, as long as the speed is constant.
Exactly. That's the key assumption.
Okay, and the very last solved example for direct proportion was all about maps.
Ah, yes, map scales.
So we had a map scale of 1 to 30 million.
Okay.
And if two cities are 4 centimeters apart on the map, what's the real distance between them?
So that scale is telling us that 1 centimeter on the map represents 30 million centimeters in the real world.
Wow, that's a huge difference.
Yeah, maps are amazing for that.
So since the distance on the map is directly proportional to the actual distance,
We can set up our ratio.
1 over 30 million equals 4 over the actual distance,
And when you solve for that,
120 million centimeters,
Yeah.
which converts to 1,200 kilometers.
so map scales are like a perfect everyday example of direct proportion.
Yeah.
They let us represent these massive distances on this tiny little map.
It's like shrinking the world.
Exactly.
Right.
But all those relationships stay accurate.
Okay, so then there was a quick example about car parking charges,
Oh, yeah.
and it gave a table showing the parking time and the cost.
Okay.
So 4 hours for your euro, 8 hours for 100 euro, 12 hours for 140, and 24 hours for 180.
Okay, so it seems like the longer you park, the more you pay.
Right. But is it a direct proportion?
That's the question, right?
Yeah, so what do you think?
Well, if we calculate the ratio of the charge to the time for each entry,
Okay.
we see it's not consistent.
Uh-oh.
For 4 hours, it's 15 per hour, 60 divided by 4.
Right.
But for 8 hours, it drops to 12.50 per hour,
Okay.
100 divided by 8, and it keeps decreasing.
Interesting.
So this tells us that while the parking fee generally increases with time, it's not a simple direct proportion. There might be different pricing tiers or other factors at play.
Yeah, so it's not always as straightforward as it might seem.
Exactly. Real-world pricing can be tricky.
And there were also quick mentions of a paint mixture problem, 1 part red to 8 parts base,
Yeah.
and a soft drink factory problem.
Okay.
They make 840 bottles in 6 hours.
So these are presented as situations where direct proportion could come into play.
Yeah, encouraging us to see these relationships in lots of different places.
It's about recognizing those connections.
From mixing paint to running a factory.
Direct proportion is everywhere.
Okay, now let's move on to the second big idea.
Right.
inverse proportion.
That's where things get really interesting.
So in inverse proportion, when one quantity increases, the other decreases, but not in just any way.
No, it's very
Like
specific.
their product remains constant.
That's the key difference from direct proportion, where it's the ratio that stays the same.
So it's like a seesaw where if one side goes up, the other side has to go down to keep it balanced.
Exactly. That balance is maintained by the constant product.
Okay, the example that was given was about Zahida going to school.
Okay.
So the distance to school is always the same.
Right. Fixed distance.
But if she increases her speed, like if she runs instead of walks, the time it takes her to get there decreases.
Of course, the faster you go, the less time it takes.
Yeah, so if she doubles her speed, the time is cut in half.
Right.
If she triples her speed, the time becomes 1/3.
That inverse relationship is key.
And the material points out that, like, the factor by which the time decreases is the inverse of the factor by which the speed increases.
Right, so if speed goes up by a factor of n,
Okay.
the time comes down by a factor of 1 over n.
So they're, like, perfectly balanced.
They are, and that ensures that the product of speed and time,
Which equals distance,
right,
stays the same.
because the distance to school isn't changing.
So another example was about textbooks.
Okay.
A school has a fixed budget of 6,000 euros for textbooks. So if the price of each book goes up, the number of books they can buy with that same budget decreases.
Yeah, they can afford fewer books.
Right. So if each book costs 40, they can get 150 books.
Oh.
40 times 150 equals 6,000.
Right.
But if the price goes up to 50 per book, they can only get 120 books.
50 times 120 is still 6,000.
So in both cases, the total amount of money spent stays the same.
It's just that balance between price and quantity.
Yeah, so instead of xy equals k, we have x multiplied by y equals k.
Right, where k is that constant product.
Yeah.
That's the defining feature of inverse proportion.
Okay, and the material also mentioned if you have two sets of values by 1 and y1 and y2 and y2, then my 1 times y1 will be equal to by 2 times y2.
Right, that's the mathematical expression of that constant product.
Which can also be rearranged as by 1 by 2 o by y2 y1.
Yeah, you can express it in different ways, but the core concept is the same.
Okay, so then there was this hands-on activity with counters.
Oh yeah, do this for inverse proportion.
You take a fixed number of counters, like 48,
Okay.
and arrange them in rows on squared paper.
Okay, I'm visualizing it.
So as you increase the number of rows, the number of columns you need to fit all 48 counters decreases.
Yeah, because you're spreading them out more.
Exactly. So the table showed 2 rows need 24 columns.
2 times 24 is 48.
3 rows need 16 columns.
3 times 16 is 48.
4 rows need 12 columns, and so on.
Always 48.
And what stays the same in all these arrangements?
The product.
Yeah, the product of the number of rows and the number of columns C.
Always equals 48.
So R times C equals 48.
Perfect example of inverse proportion.
And the activity also asked about the ratio of 2 row numbers and whether it's the inverse of the ratio of their corresponding column numbers.
And it is, right?
Yeah.
Like if you compare 2 rows to 4 rows.
A ratio of 1 to 2.
The ratio of their columns 24 to 12 is 2 to 1.
It's flipped.
It's the inverse.
Okay, so then there's a try these section with 3 tables.
Let's see what we've got.
In the first one, X decreases from 50 to 20, while Y increases from 5 to 8.
Okay, so if we check the products, 50 times 5 is 250.
Right.
But 40 times 6 is 240.
So different products.
Not an inverse proportion.
What about the second table?
Let's have a look.
X increases from 100 to 400,
Right.
and Y decreases from 60 to 15.
100 times 60 is 6,000.
Okay.
200 times 30 is also 6,000.
Ooh.
300 times 20, still 6,000.
Wow.
And 400 times 15. Yes, 6,000.
So consistent product.
This is definitely an inverse proportion.
Okay, last one. X goes down from 90 to 5,
Okay.
and Y goes up from 10 to 35.
90 times 10 is 900.
Uh-huh.
60 times 15 is 900.
Okay.
45 times 20, 900.
It's looking good.
But 30 times 25.
Is 750? Inconsistent product.
So not an inverse proportion.
Nope.
Okay, let's go through the solved examples for inverse proportion.
Yeah, these are always helpful.
So first one is about pipes filling a tank.
Okay.
If 6 pipes take 80 minutes to fill it, how long would it take if you only used 5 pipes?
So fewer pipes means it'll take longer.
Right.
It's an inverse relationship.
So we can use that idea of the constant product.
Yeah.
Number of pipes, 1 times time, 1 equals number of pipes, 2 times time, 2.
So 6 times 80 equals 5 times x.
And solving for x gives
Yeah.
us
96 minutes.
96
So
minutes.
it takes longer as expected.
Yeah.
And this really shows how the total work to fill the tank stays the same.
It just takes longer with fewer pipes.
Whether it's more pipes for a shorter time or fewer pipes for a longer time, the total output is constant.
I like that.
It's a nice way to think about it.
Okay, the next example was about food supplies in a hostel.
Okay.
So if 100 students have enough food for 20 days,
How long would that same amount of food last if 25 more students joined?
okay, so more mouths to feed.
Yeah, so the food is going to run out sooner.
Definitely another inverse proportion.
So we use our formula, initial number of students times initial number of days equals new number of students times new number of days.
So 100 times 20 equals 125 times a U.
And solving for Hay gives us
16 days.
16 days.
Makes sense. The food won't last as long with more students.
It's a good illustration of how inverse proportion works in like real-world resource allocation.
Exactly, when you have a fixed amount of something and the number of consumers changes.
Okay, last solved example. This one's about building a wall.
Right.
So if 15 workers can build a wall in 48 hours, how many workers would be needed to finish the same wall in 30 hours?
So less time means you'll need more workers.
Exactly. It's an inverse proportion.
Because the total work building the wall doesn't change.
Right.
So we have initial workers times initial time equals new workers times new time.
15 times 48 equals y times 30.
And solving for E gives you
24 workers.
24 workers.
So you need more people to get it done faster.
It's that classic trade-off between workforce and time.
The material also mentioned a few other examples.
Oh, yeah.
Like dividing prize money,
Yeah.
the spokes on a wheel,
It's okay.
and sharing a box of sweets.
These are all great real-world scenarios where inverse proportion applies.
Like if you increase the number of winners, but keep the prize money the same.
Each winner gets a smaller share.
Right. Or if you add more spokes to a wheel, but the wheel stays the same size.
The angle between the spokes decreases.
And if you have a fixed number of sweets and more kids to share them with.
Each kid gets fewer sweets.
So it's all about these like balanced relationships.
Exactly. It's fascinating how widespread this principle is.
So we've really explored two key ways things can change together.
Direct and inverse proportion.
And like recognizing these basic relationships can be super helpful.
Totally. It gives you a way to understand and solve so many everyday problems.
Without getting lost in the formulas.
It's about the concept.
Exactly. And it's all thanks to your materials.
It's been a great deep dive.
Yeah. So now that we've got a good grasp on direct and inverse proportion, I'm kind of curious about other kinds of relationships.
Yeah, me too.
Like what about situations where things change together,
Okay.
but neither their ratio nor their product stays constant?
Right. Like more complex relationships.
Yeah. What might those look like?
It's a good question. Something to ponder.
Maybe they're all around us and we just haven't noticed them yet.
Now that you mention it, I bet they are.
It's like a whole new way of seeing the world.
Exactly. Keep your eyes peeled.
And your mind open.
Absolutely.
Thanks for joining me on this deep dive.
It's been a pleasure.
Until next time.
See ya.